All right, so now we're going to talk about interference in thin films, and it's going to describe and explain why that oil slick in that crappy part of the parking lot looks so freaking beautiful when it has no right to look that beautiful. So let's, I'm going to start drawing a diagram. Let's consider two thin sheets of glass separated in like a wedge-like shape. So here's one. And I'm gonna give it some thickness, but we'll ignore the thickness for simplicity. But I'm gonna draw it as it is. So then separated by just a little bit, give that one a little bit of thickness too. Okay, so we have these two sheets of glass. This has an index of refraction of glass, which is like maybe 1.6 depending on the glass, and then in between you have air, index of refraction of like 1. So what we're going to consider, here I'll draw some of these here. So this has thickness T, and this we're going to say is length L. It's my little cursive L that sometimes ends up looking like a 2. That's an L. And we're going to consider two rays. So one of the rays, so there's like a total amount of light that's coming in here, right? And I'm going to do it off to the right just a little bit. Total amount of light coming in, and some of it reflects at this interface here, which is the one of the top slab that we're not ignoring. And it reflects, right? And then there's some other portion of the light that does not reflect. It goes through, and the line's just a little bit too long. I can't make it any shorter, but it reflects on this bottom interface, and we're going to say that the slabs, the wedge, that angle is so small that these are basically parallel here. All right, and I'm going to say that this length here is x. Okay. So we have two reflections. The first is at the glass-air interface, and that's the yellow one. And the second is at the air-glass interface, so like going from air to glass, and that's the purple one. The index of refraction of glass higher than that of air, and remember these reflections are analogous to mechanical wave reflections. So I want to pause on this for a sec. When we went over mechanical waves on a string, I continuously have tried to sell you on the fact that mechanical waves on a string are more important than just mechanical waves on a string. So it, allowed us to develop the formalism and the mathematics of waves, and that applied kind of, throughout a little bit. But there's a very specific analogy that I only came across recently with this that can help from our intuition about mechanical waves on a string, can help inform intuition about reflections at interfaces like this, optical reflections. So for the first reflection from glass to air, this is like a mechanical wave going from a heavier rope, right? Higher index of refraction, thicker rope, heavier, more mass per unit length of rope, to a lighter rope. And in this case, there's no inversion. And you can look up videos and see a wave pulse that somebody has instigated on a rope. You can see that if it goes from a heavier rope to a lighter rope, it's not very good, but it is a heavier rope, to a lighter rope, this wave pulse, as it travels, it will reflect and not invert. So no inversion. But in the opposite scenario, lighter rope, and that's because, so we kind of covered it in our lecture as like a string that's attached to a ring that's allowed to move vertically on a pole. So it like, it's traveling, and then the ring moves up, and then the ring moves back down, and then it comes back and travels back. No inversion. So that same thing would happen here if there was a transition between heavier rope and lighter rope. And I want to draw the kind of analogous connection between rope thickness kind of analogously applying in terms of, wave reflections and inversions of phase, applying, being equivalent to index of refraction. So if you're stepping up in rope thickness or stepping down in rope thickness, it's the same conceptually in terms of what happens with the phase of the wave. Does it invert or does it not invert? To if you're stepping up in index of refraction or stepping down in index of refraction for an optical wave, right? So like then if we went from a light rope to a thick rope, this wave pulse that we might instigate would then come back underneath. It would flip. And that, in our lecture, we kind of covered that as a rope that's attached to, it's like stuck on to this wall here. And so the wave pulse went, and then it inverted on its way back. You remember that? So that same scenario would then happen if it was a light rope attached to a heavy rope. And you can look up videos of this. Maybe I shared one with you. And that's really interesting. So it builds intuition, because it's kind of otherwise, I think, non-intuitive why there's a phase shift in one case and not another. So hopefully that helps with some intuition. I discovered that connection recently, and it's really helpful in my head. So, so going back to our diagram here, the first reflection, the yellow, from glass to air, right? So it would be, that's the transition from glass here to air here. Whoa. That is a step down. It's a step down in index of refraction. And it's just like going from heavier rope to lighter rope. So there's no inversion, right? There's no inversion. That's kind of neat. And then for the other one, for the second reflection, the purple one, from air to glass, that's a step up. That interface goes from index of refraction of air, which is lower, than index of refraction of glass, which is higher. So a step up in index of refraction does result in a phase shift, because that's like going from a lighter rope here to a thicker rope or a heavier rope there, and it does produce an inversion, which, remember, that's analogous to this picture here that we kind of mapped out. All right, so that means that, there is an inversion for that second one. A pi phase shift produces this wave on the underside, right? Because the wave is like this, so it's a pi phase shift, okay? So that's kind of interesting. All right, so these two waves will reflect at the different points, and they will interfere. And so we have to figure out what's going to happen, right? So at different points along the wedge, we're going to refer to the following. So I'm going to type this so that's a little bit less messy. If neither or both of the, this is kind of like a rule for thin films, right? So this isn't like, first principles physics. This is like for specifically problem types of thin films. This is kind of like the flow chart, the logical flow chart of what, how to approach it, what's going to happen. So if neither or both of the reflections are phase shifted, then we have we would refer to these equations, the constructive interference would occur at 2t equal to m lambda. So that's constructive interference from thin film specifically. And that's with the same integer m being, 1, 2, 3. And the destructive interference I'll say reflection because that's what it says in the notes, but it's the same thing. So reflections that result in destructive interference in a thin film would be 2t is equal to that m plus a half. You knew that was coming. And that's for integers of m. 1, 2, 3. Blah, blah, blah. Okay. If 1, I'm going to type this again. If specifically just one and not the other of the reflections is phase shifted, it's the opposite. So those two equations apply to the opposite scenarios. So maybe I should make a table of this. Constructive, holy crap, div is 2t is equal to m plus 1/2 lambda for m equals integers. And destructive occurs at m lambda, integer multiples of the wavelength. All right. We can use these relations to determine the spacing of the fringe patterns caused by the path length differences of the two reflected waves at the front and the back interfaces of a thin film. So it's really similar, right? We're kind of thinking through similar fringe patterns as this, and we're kind of figuring out spacing similar to this y of the fringe patterns, right? But for specifically thin films, and these are the equations that apply. So maybe in your notes you can organize that in a kind of like quad table a little bit better. I guess you'd have like constructive, destructive, neither or both, and then if one, in terms of phase shifting. And you can fill those in. Maybe that would be better for your notes. I probably should have done that. Okay. This only applies to thin films. This is just kind of like a specific application, and those thin films, that would be defined as like a few micrometers or less, or micrometers. And that's because the two interfering waves are assumed to be coherent at the start, and so that means they all have the fixed phase relationship with each other. And that's only true of emitted light from like a source like the sun or a light bulb or normal sources with small distances between, small path length distances between. For thicker films, greater than a few microns, the interfering light waves, like, so if you imagine like a really thick film, right? And so like the difference here of even if it's coming in at exactly the same, the difference here, if this was like, like 2 feet or something, it wouldn't produce an interference pattern because the two light sources, they don't have the two, it's been too much time from the first, the first packet of light that is gone and reflected to a later packet of light, right? It's traveled too much time here to then end up, there's like too big of path length difference here, and it's kind of from a different packet of light from the source. And I guess that's kind of like, you hear me like struggling to describe this because this gets into things that are a little bit beyond your first year physics, but just suffice it to say that, you know, that those two don't have a fixed phase relationship anymore. So this really only applies to thin films for a few microns, and you'll find out a lot more about packets of light in future classes. Okay, so I thought that instead of just stating this, it's kind of nice to do some example problems. So I think we can do an example problem here. I'm going to, instead of pasting this in, maybe let's see, I should have prepared this before. I'm just going to type it out, and you can skip ahead if I take too long. So, suppose the two glass plates in the figure that I'm going to draw are two microscope slides 10 centimeters long. At one end, they are in contact. At the other end, they are separated by a piece of paper for 0.02 significant figures thick. What is the spacing of the interference fringes seen by reflection? Is the fringe at the line of contact bright or dark? Assume, as we do, monochromatic light with a wavelength in air of, let's see here, insert equation, lambda equals lambda naught equals 500 nanometers. All right, so now I'm going to draw the diagram. Hey, that wasn't so bad though, huh? Pretty good at typing on an iPad. So the diagram's going to be very similar. So maybe I copy this one, and we just change what we need to. Boom, look at that. All right, so L is going to be 10 centimeters. We don't need X after all. We have a height. I'm going to delete this N air so I can put the height here. Height is equal to 0.0200 millimeters. We have thickness T, we have the wavelength equals 500 nanometers. So this is original wavelength. Wavelength changes somewhat when it goes through materials, right? Actually, we do need X. It was hidden in my diagram. All right, so that's all the information. So we consider the reflection. So this is a similar situation that we were talking about before, where that's, you know, both of these are glass. This is, oops. This is glass, and then there's air in between. Okay. So reflection 1. We're going from index of refraction of glass to index of refraction of air. And so that is a step down, and so there is no phase shift. Reflection 2, we're going from air to glass, and that is a step up, And so there is a pi phase shift. So one of the reflections are phase shifted. Yeah? And so that means that if you look back in your notes, what we're going to use is the constructive one is 2t is equal to m plus 1/2 lambda, and the destructive one is 2t is equal to m lambda. So that's our set, right? All right. So if we look at that x, right, and that t, we can imagine a, and we're going to say that the t is kind of, even though it's a wedge, that t is kind of applying to like where the reflection is. I just can't draw and make it, well, I'll draw. All right, so that's, it applies to over there. So we can see a triangle out of that, right? We can see a triangle out of that, where this is x, this is t, and we can see another triangle that's larger, where this is 10 centimeters, and this is 0.0200 millimeters. Or I'll do symbolically because it's better. This is L, and this is H. So, and the angles are the same. So we can do a similar triangles kind of thing. So as t is to x, h is to L. And we can rearrange that, solve for t, x, h, L. L. Right? And in this case, x can describe that fringe spacing. So x is kind of the spacing of the fringes. So let's target destructive interference using this equation here. So I'm going to insert our t for our t here, and we have 2xh over L is equal to m lambda. We could use the other one, but might as well use the one that doesn't involve the 1/2, and you can solve for where there's destructive interference, you know, the dark fringes, or you can solve for where there's constructive, the bright fringes. You still get the spacing in between, so we're just going to use the slightly simpler one. That's why we do that. And then we solve for x, and so check me on this maybe, but m lambda naught L over 2h for m equaling integer multiples. All right, so the fringes are spaced this apart, right? And if you want to get a specific fringe, right, you would plug in a given m. So m equals 0 gives x equals 0 where the two slides touch, right? So if we plug in m equals 0, that gives x equals 0, and x equals 0 right here, where there's contact between the two plates. So that was part of the question. Is the fringe at the line of contact? So that would be the line of contact, like into and out of the page there. Is it bright or dark? And so since x equals 0 when m equals 0, that means that there is a destructive dark fringe at the interference line of contact, right? Because if we were to use the other one and you plug it in, you would get x equals 1/2. So at x equals 0, it's destructive. Okay, so a couple things to note. If we used a larger wavelength, like say red light, the fringes would be more spread out. See if you can think your way through that one. And if we used white light, the reflected light would be a bunch of different things. It would be a cycling pattern through the color spectrum, where at each point, the wavelengths that interfere constructively would be most prominent, and those that interfere destructively are most absent or least prominent or dim, right? So because there's this wavelength dependence here, if you have like a whole spectrum of light, right? I don't know why I drew a box to describe the spectrum of light, but if you have if you have white light shining at our film here, there's all kinds of wavelengths that are all at the same time simultaneously doing this. And so you will see as this wedge shape, right, as the thickness kind of changes, you'll see different colors at different locations X along the film. If it was the same thickness, right, and film kind of like this, and you had, things going like this, and it was white light, you would get specific color would be most prominent and everywhere, and a specific color, would be least prominent, and so you get that whole film kind of appearing a certain color, and you can see this in uniform thin films. But since it's this wedge pattern, it kind of helps show in a little bit like cleaner, more uniform way, or like constant slope kind of way, that you would get a sweeping through the color spectrum at different thicknesses that that result in constructive and destructive interference. So you'd get like varying colors. So in an oil slick on the crappy part of the pavement, the thickness of that film is small enough to be a thin film, and it's not completely uniform. It's not like completely flat. And so, especially, if the ground is not perfectly flat, and so you have these variations in thickness, which result in variations in constructive and destructive interference from reflections from the white light from the sun. So depending on how you're looking at it, depending on what part of the oil slick you're looking at, you can see all kinds of different monochromatic, all kinds of different colors, or multichromatic is what I mean. So that's kind of neat. Okay, so that was like, almost didn't even seem like a real problem because it was exactly the scenario as before, right? So I want to evolve this a little bit. So now let's suppose the glass plates in the previous example we just did have n equals 1.52, and the space between plates contains water, which n equals 1.33 instead of air. What happens now? Okay, so the situation has changed. The geometry is the same, but now we have a specific index of refraction of the glass. So we're going to say 1.55. And this is no longer air, this is water, which is, they're saying 1.33. Okay, so now we're going to go through our two reflections and we're going to see what happens, right? And this is also 1.55. Okay, so for the yellow reflection, the first reflection, we're going from 1.55 to 1.33. So that is a step down in index, and a step down in index means that there's no phase shift. So I'm going to just write in yellow here, no phase shift. And then for the other one, we're going from 1.33 to 1.55, and there's again a step up, and so we have a pi phase shift. So no different. But what is different? Well, the wavelength of 500 nanometers here going in is the original wavelength in air, but at the point of reflection here in the thin film, this inner part, I'll do blue, being the thin film, right? That's the wavelength that these equations apply to. So in there, the wavelength is not going to be 500 nanometers, right? So it's a little tricky in that sense, that we have to be careful of the wavelength and use the proper wavelength. So if we recognize that, this wavelength inside film is equal to that divided by the index. So 500 nanometers divided by 1.33, the index of the film itself, which is about 376 nanometers. And then you plug in just the same. So you just kind of have to catch that. Make sure you're using the wavelength from inside the film that you're talking about. And I won't do a lambda naught anymore. You can do a lambda W if you want, lambda water. But that's what you would plug in. Okay, so I'm going to evolve this one more time, and this is the one that you were probably expecting. This is the one that I was expecting, where we have different kind of index situation going on. So finally, suppose the upper of the two plates is a plastic with n equals 1.40. The wedge is filled with a silicone grease with n equals 1.50. And the bottom plate is a dense flint glass with n equals 1.60. Equals 1.60. What happens now? Silicone. Okay. Now we're going to evaluate. So we have the first one is our yellow one. What is this word supposed to be? Plastic. This is supposed to be the word with. That's funny. Okay. First one goes from 1.4 to 1.5. So that's a step up. So there does invert, right? It's like thinner rope to thicker rope, and it does invert, right? That's what I'm thinking through in my head. Otherwise, it's just a memorization thing. But if you see demonstrations of the mechanical wave on a rope, or if you kind of like had thought that through and got that intuitively into your head, then it makes this real quick. The wedge is filled with silicone grease, 1.5, so then it goes from 1.5 to 1.6, which is yet another step up. So then for the next one, purple I guess, does invert again. And so therefore, back in our little table here, if neither or both the reflections are phase shifted, then we use these equations. And so we're going to use these, and I'll write them down here. Constructive 2t is equal to m lambda, and destructive would be the other one. 2t is equal to m plus a half lambda. Okay, and the question was, what happens now with all of this? Okay, so now we have a low to high index and another low to high, so both reflections are phase shifted. So we're going to use the simpler one still, but we have to note that now this simpler one, and by that I mean just the m and not the m plus a half, that refers to constructive interference instead of destructive interference before. Right? Before we were defining destructive interference with the simple one. But now, since we're in this different index kind of like regime, we have constructive interference for the simpler one. Okay, so 2t is equal to m lambda. That's what we're using. So then you would do a similar thing where we find So from like triangles, right? You'd have the t over x is equal to h over l, and that solve for x, and you get TL over h. And then we use this guy, we can solve for t. It's equal to m lambda over 2. And we can plug that in here, and we can get x is equal to m lambda l over 2h. But specifically, this lambda, as we just kind of got a warning about, is the wavelength in the grease of the silicon grease, n equals 1.5. So the original wavelength divided by n, so that would be 500 nanometers divided by 1.5 index of the silicon grease, and that turns out to be about 333 nanometers. So with this being the lambda that we're going to use, and you can compute that. So that is the spacing, if you can compute all that. And now, note though that for this, m is equal to 0, 1, 2, 3, blah, 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 m equals 0 refers to x equals 0, the point of contact for these plates, x equals 0. But now that refers to constructive interference, because that is the equation that we're using, the constructive one. So m equals 0, or at x equals 0, where the plates are in contact, there is constructive interference. Constructive. I'll say, yeah, interference, or a bright fringe, in other words. All right. And then I'm just going to qualitatively mention and just kind of like talk through 2 applications of this thin film reflection thing. So if you're interested in astronomy, this concept of thin films and the reflections of such is involved in the process of making lenses. I guess that applies to much more than astronomy, but I always think of like perfect lenses applying to these like 10-figure telescopes, and it has to be absolutely perfect. So anyway, so in lens constructive and also in anti-reflective coatings. But for lens construction, a lens is made by grinding a solid disc of glass against the master. And my copy-paste is failing me, so I'm going to try to just like draw this real quick. Think of this as like a kind of grinding bowl that kind of has like some depth to it. I don't know even how to draw that, right? And then your piece of glass that you're wanting to turn into a lens, it might start off like a cylinder like this, and you're going to grind it in there. Oops, that's pretty terrible. You're going to just grind it down until it matches the master. So from a top view, so yeah, like this might be spinning or something at a high RPM for like hours or something, I don't know. But from the top view, if you were to look straight down on it, you would see the master, being out here, and the thing there, and you would see, let's see, I'm going to attempt to draw, but you would see like, certainly not uniform, but you'd see like this topology of rings that might indicate, so these are interference patterns, these are fringes, and the spacing is different because the thickness is different, right? And this would describe how far off you are from the master and the spots that need to match. And so, so if you shine a light on it, it would reveal this fringe pattern, and it would indicate the parts that need more precise grinding. So that's kind of neat. Let's see. There's one more thing, that the little tidbit. It says at 10 lines from the center spot, the distance between the two surfaces is 5 wavelengths, or about 0.003 of a millimeter. It's like 3 microns. This isn't very good. High-quality lenses are routinely ground with a precision of less than 1 wavelength. The surface of the primary mirror of the Hubble telescope was ground to a precision of better than 1/50th of a wavelength. Unfortunately, it was ground to incorrect specifications, creating one of the most precise errors in the history of optical technology. It's scary how often that happens. Check your units and make sure that you're using the same units as your collaborators in the UK or wherever else in the world. Okay, the second application is anti-reflective coatings. You can coat a surface, like a window or your sunglasses or something, with a thin film of a specific refractive index and thickness, and you can engineer it such that the destructive interference of a certain wavelength, that there is destructive interference of a certain wavelength, so that you can kind of cut out reflections on your glasses or on your window on your building. So often these films are applied to like target the large greenish middle zone of the spectrum that is emitted from the sun. So you kind of like destructively interfere most of the photons that are coming from the sun, and so therefore it cuts out most of the reflections, and that would be anti-reflective coating. If you could somehow control the room or the environment to be like one, like not white light, but like a colored light, then you can engineer a thin film or an anti-reflective coating to be completely anti-reflective, because it would, perfectly apply to that wavelength. So that's kind of cool. And then a third application of this concept of optical interference is the Michelson-Morley interferometer. It's a concept, or maybe a free space optics setup, or maybe an instrument, you might say, that allows you to tell like really, really, really small topological distances from the fringe patterns that the light makes from a reference beam that does not reflect off of the object that you're choosing to look at, interfering with one that does. So I'm just going to draw this real quick, and we won't talk about this forever. But if you have a splitter here, and the light kind of goes through, I'll draw it accurately, and then you have this plate, which is to help with the path length difference so that they're exactly the same. And then this is a mirror, so a fixed mirror. I'll say fixed. And we have, this was a splitter, so we're going to say it reflects here, and then it goes, that wasn't very good, reflects here, refracts, goes, oops, gosh, reflects, refracts, goes up, and now you have a moving mirror, right? Now that light, like, it'll start here, go here, then turn around, right? This one at the top, it goes up, and then it turns around. And because of this guy, you're taking into account the path length difference that the top one went through this twice, whereas the bottom one just straight reflects there at the surface. And so we call that a compensator plate. And this is a beam splitter. Super common component if you work in an optics lab is mirrors, beam splitters. Compensator plate, I guess, is just like a specific thing for this. But and then, you observe with your eye here. Give them eyelashes. You observe. And so the two rays combine. And since they're overlapping, if they're in phase, they will constructively interfere. If they're out of phase, they will destructively interfere. And so, based on the wavelength of light that you are using, if those path lengths are exactly the same, you know that they would constructively interfere. And so if the mirrors are slightly off in either angle, then they either angle or distance or whatever, then they play the role of a thin film wedge, and you get a fringe pattern. So the idea is you kind of tilt one of the mirrors, and you can count fringes, and the wavelength of light, and so you can convert those fringes that pass across your view of like in the microscope or something, or on the screen if the light is being received by a CCD, which would be more common. And if you know the wavelength and you've counted the fringes, then you'd have a measurement of a very, very small distance that you've moved the mirror, accurate to a half wavelength of light that you used, because you have accurate, between dark and bright fringe. Beyond that, you don't know, but yeah. And so you can place something on the mirror, and you can kind of like see what the topographical height difference is based on, like, you can place a little tiny, like, I don't know, something that's like a few microns, whatever that may be, like little beads or something, little nanoparticles perhaps. If you use the right wavelengths, you can tell nanoscale, and you can just like map out the topology to a very, very, very accurate degree. All right, so anyway, that's cool. That's the last thing I wanted to talk about, and so that is it for interference. What I would recommend is studying this two-source interference of light in depth, because you'll find that this kind of concept will apply directly to beyond.